welcome to episode 1 of chapter 4. We're going to be starting work, and this is going to cut into also integration in multiple dimensions as well. So, let's suppose you have some particle moving in some. So this is where we're going to start cutting more into some of this vector calculus stuff. Suppose we have a vector field, okay? Vector field F. And we have a path along that field. From B, A to B. And this path is parameterized by this parameter T. Okay? So if we want to know how, let's suppose we want to know how much of this particle's movement along this path was a result of that force. Well, if we zoom in, we're going to have we're going to have an infinitesimally small, so I'm going to call this path S, infinitesimally small change in our path, and here's our force, right? So if we want to know how much of that this change is a result of that force, well, this is we can use a vector projection. This is the projection of F along ds, right? Or better put, F dot ds, right? And so if we took let's say multiple points, multiple segments along this curve, right? Then we would simply add up all of the segments along the curve. And as that limit, so as this sum approaches, as the limit of our segment approaches infinity, this is going to approach an integral from A, because remember, an integral is an infinite sum, from A to B of F dot dr. F dot dr, which is the whole path, right? And F is going to be obviously a function of x, and this is going to be our position. And this integral here, this is called a line integral. This is called a line integral. And this relationship between a force field and a path is called work. So this is the work, W, done by force F on this particle as it travels along this path. Right? So let's think about how we can evaluate this integral. I'm going to go into more in depth of evaluating line integrals in a separate video. But one way we can evaluate this as well, we want to put this under a common thing. So let's go. So this x, we're going to basically perform a transformation. We're going to basically parameterize x as this r of t. And then what happens to this r of t? Well, remember we did the chain rule. What is dr? Dr is going to turn into r dot t dt. And we're going to get this integral from a to b of f of r of t of r dot dt. and this is equal to our work. And another thing we can do is we can use the what I'm going to call the fundamental theorem. Theorem of calculus. For line integrals. So what do I mean by that? Well, let's think about what the fundamental theorem tells us. With an integral from 0 to t of d over d, probably should have put a better variable. So let's say this is x of d over dt of f of t dt. This is equal to f of t, right? Or more generally, if we have our bounds, or this is f of x. More generally, if we have bounds a and b, then we have the exact same thing. Then we have our answer is f of b minus f of a. So if you remember, in multiple dimensions, we do not have the same notion of derivative, but we do have a gradient. So we don't have d over dt. Instead, we have the gradient. So what this fundamental theorem of calculus for line integrals tells us is if we have this integral of a negative of delta f over dr is equal to f. So if we have f equals nabla f over b and a, f of b minus f of a. And that's what that tells us. So if you remember, we have what's called a conservative force. This means that we can derive the force from a potential energy. Right? Some potential energy. This means that if f is conservative, so if f is conservative, then our work is equal to ba negative delta u dr, which we know from this theorem, this is the dot product, from this theorem is going to be equal to negative u of b minus u of a, which is u of a minus u of b. And so what is that? Well, this is the change in u. So we have work is equal to the negative change in potential energy. So hope that makes sense. In the next stage, we're going to use this and look at what's called the actually, first we're going to look at this in terms of gravity, and then we're going to look at using this and deriving the work energy theorem. So